The reason why different athletes are suited to different sports is because of the muscle fibers they have. In figure 1, it clearly states the percentage of fast glycolytic and slow oxidative muscle fibers that someone has depending on what event or sport they play. Every athlete will have an element of 3 muscle fibers in their body. However, during physical activity, some of these muscle fibers will work and present themselves more than others to produce the result the athlete wants. But this is depending on the quantity of different muscle fibers the athlete has in the first place. An example of this is in an endurance event. The reason why the athlete needs and has a high percentage of slow oxidative muscle fibers is because the event requires the athlete to run at near enough the same intensity for long periods of time. So the characteristics of the slow oxidative muscle fiber suits this event perfectly. These muscle fibers' contraction rate is slow, but their fatigue rate is low too, because they respire aerobically, meaning more oxygen is supplied to the working muscles over long periods of time. In addition to this, the other muscle fibers are also used. The fast oxidative glycolytic muscle fiber is used when in transition from the fast glycolytic muscle fiber to the slow oxidative. So when there is a sprint finish at the end of the endurance race, the fast glycolytic muscle fibers will contract so that the athlete generates more speed. But when these start to tire and fatigue, that's when the fast oxidative glycolytic muscle fiber is used, and as its characteristics have elements of slow oxidative muscle fibers and fast glycolytic muscle fibers. So this will help the athlete to continue in the rest of the race at a moderate speed. Athletes that are jumpers, so that includes triple and long jumpers, have a high percentage of fast glycolytic muscle fibers. This is because the athlete requires their muscles to contract quickly in order for them to generate power and speed, to build up momentum, so that when they jump, their momentum carries them a long distance. But also, these events are over within seconds, so the muscles that are contracting don't need to contract for long periods of time. These muscle fibers contract very quickly but have a very high fatigue rate as they respire anaerobically, which means oxygen gets supplied to the working muscles but only for a short period of time. In conclusion, the properties of the fast glycolytic muscle fiber are perfect for this type of athlete. However, the athlete will still use all of the other muscle fibers, as they will use the slow oxidative muscle fibers at the beginning of the event, as these muscles are normally employed first. We did an experiment by which we used a specialized exercise bike to record the motion of the participants' ride in 3 minutes to establish what muscle fiber types they had, whether that be fast glycolytic, fast oxidative glycolytic, or slow oxidative. With Megan, the graph indicates one significant decline in power output, and then the rest of her ride is suitably stable, suggesting that this participant has more slow twitch muscle fibers, as the characteristics of slow oxidative muscle fibers include slow contractions but with a low fatigue rate. And judging by Megan's graph, her fatigue rate is low as there are no sudden spikes in the graph, implying that there is no fast glycolytic muscle fibers contracting. However, fast glycolytic muscle fibers can be seen at the very start of the ride, as they recruit a high power output, and the power output is very high, as her peak power output is 6.007 watts per kilogram. But then we see it dramatically decreases. This is because the characteristics of the fast glycolytic muscle fibers have a very high fatigue rate. Fast oxidative glycolytic muscle fibers can be seen when transitioning from the fast glycolytic muscle fibers to the slow oxidative muscle fibers. This is when we see a gradual decrease in the graph because the muscle fibers are transitioning from working anaerobically to aerobically. In conclusion, Megan has more slow oxidative muscle fibers. This is because her average power isn't very high and her graph is shown to be steady throughout the ride. However, in contrast, Georgia's graph shows significant increases and decreases in power output, meaning that this would indicate that Georgia has a high percentage of fast glycolytic muscle fibers because the properties of these fibers suit the description of the graph. The fiber's contraction rate is very high, meaning that average power output should be high, and in Georgia's case, it is 2.6 watts per kilogram. Also, these muscle fibers fatigue very quickly, and as you can see of Georgia's graph, there is a sudden increase and decrease in her power output, meaning that the recruited muscle is fatiguing. In the meantime, the fast oxidative glycolytic muscle fibers take over because the graph shows that the power output is moderate, and this is one of the characteristics of the fast oxidative glycolytic muscle fiber. The reason why Georgia hasn't got many slow oxidative muscle fibers is because there is no major decrease in power output that stays constant throughout the ride. In conclusion, Georgia has more fast glycolytic muscle fibers because you can see where the muscle fibers fatigues and then it is recruited again. Isotonic contraction consists of two types of contractions, concentric and eccentric. Isotonic contraction is where movement happens either concentrically or eccentrically, but the tension of the muscle contraction stays the same, just the length of the muscle changes depending on the movement. Eccentric contractions happen in the hamstring during extension of the leg at the knee, when an athlete is taking a shot in football. Or in contrast, concentric contraction happens in the hamstring when an athlete flexes his or her leg at the knee in preparation to kick a football. Concentric muscle contraction is where the muscle length is shortening, so as it shortens, it generates enough force to move an object. For example, flexion of the arm at the elbow when lifting a weight. The bicep brachia shortens, causing it to swell through contraction, enabling the weightlifter to lift the weight towards them. Also, when a gymnast is in the upward phase of a press-up, the pectoral major contracts concentrically as the muscle shortens. In eccentric contraction, the muscle length is increasing. Muscles increase in length in response to a greater opposing force. An example of this is the extension of the arm at the elbow during the lowering stage when a weightlifter has finished his or her routine. The bicep brachia lengthens as it contracts in order for the athlete to have control over the weight when lowering it. This is because gravity is naturally pulling the weight to the floor, so without eccentric contraction, the weightlifter would drop the weight. Another example of eccentric contraction is during the lowering phase of a squat, when the athlete in football is doing dynamic stretches to warm up before a match or training session. During a squat, when lowering, the gluteus maximus muscle contracts eccentrically. During isometric contraction, the muscle length is the same. No limbs are moving. The muscles are still contracting but are causing no movement. For instance, the crucifix in gymnastics, all the muscles in the arms and shoulders are contracting to hold the gymnast up, but the athlete's arms are not raising or lowering, so this is isometric contraction. In addition, the rectus abdominals contract during the exercise of the plank to keep the athlete stable, but no movement occurs, meaning that the rectus abdominals are contracting isometrically. Muscles work in pairs, so in every skeletal muscle contraction, there is an agonist and antagonist. The agonist is the prime muscle that is contracting, while the antagonist is the opposite muscle that is relaxing. An example of this is during a running action. There is flexion of the leg at the knee, so the agonist is the hip flexors as these muscles are contracting, whereas the antagonist is the gluteus maximus as this muscle is relaxing. The synergists are muscles that work together to enable the agonist to work more effectively. They prevent undesirable movements from occurring and help the movement happen. For example, when doing a bicep curl during the movement of flexion or extension, the muscles around the elbow joint, such as the brachioradialis and the brachialis, work together so that the bicep or tricep can work more effectively during contraction. Fixators are muscles that are located around the origin. They help stop unwanted movement by stabilizing the origin joint so that the agonist can achieve full muscular contraction. The quadricep would be an example of a fixator during plantar flexion of the ankle, as these muscles stabilize the origin, which is the femur, while the agonist, so the gastrocnemius, contracts. The sliding filament theory is a theory that suggests how our muscles contract in order to create movement. Each muscle fiber is made up of contractile protein, myofibrils, and the basic unit of striated muscle is known as the sarcomere. Within the sarcomere, there are thick filaments called actin and myosin. During a contraction of a muscle, myosin filaments attach to the actin filaments by forming chemical bonds called cross bridges. When these connect, the force generated by the myosin gets passed to the ends of the muscle fibers when the actin filaments join with the myosin. The theory involves the actin filaments proceeding to constantly bind and reattach and let go of the myosin. The process of binding then reattaching allows the muscle to shorten, so contract. When there is no muscle contraction, strands of protein called tropomyosin and a molecule called troponin link together and are attached around the actin filaments to stop the myosin binding together with the actin. Then, when a muscle wants to contract, calcium ions are introduced to the muscle cells. The calcium flushes out the tropomyosin and troponin, allowing actin to be exposed. It does this by changing the shape of the troponin, causing the tropomyosin to move. With actin free, the myosin combines with it. The muscles contract according to the sliding filament theory. However, muscles can't consistently contract without ATPase, as this enzyme enables a quick supply of energy for a muscle contraction. The motor unit is how muscles receive the messages which enable them to contract. Firstly, the receptor, so the skin or eyes, detect a stimulus which triggers an electrical chemical signal to be sent along the sensory neuron to the central nervous system. The relay neurons carry the message in the central nervous system to the motor neurons. The motor neurons attached to the skeletal muscle fibers so that when the action potential conducts the nerve impulse down the motor neuron and into the muscle fibers, the muscles contract. In the motor neuron, the axon passes the signals down at the point where the neuron and the muscle fiber meet, which is known as the neuromuscular conjunction. At the neuromuscular conjunction, there are 2 points known as the axon terminals and the motor end plate. These parts help the positive electrical impulse get through to the muscle fibers. But there is a small gap between the neuromuscular conjunction and the muscle fiber, which is called the synaptic cleft. At the synaptic cleft, acetylcholine is secreted, and with enough acetylcholine and electrical charge, there is the potential for muscle contraction to happen at the particular muscle fiber. The all-or-nothing principle is a principle where if an action potential creates enough electrical charge that reaches the threshold, then all of the muscle fiber in that motor unit will contract at exactly the same force across the entire motor unit. Whereas if not enough electrical charge reaches the threshold, then absolutely no muscle contraction will take place. A sporting example of this would be in tennis. So the receptors, so the athlete's eyes, detect the stimulus, so the ball. This message gets sent along the sensory neuron to the central nervous system. Then in the central nervous system, the relay neuron carries this message to the motor neuron. The axon carries the message down to the neuromuscular conjunction, where combined with the electrical charge and the acetylcholine that is secreted from the synaptic cleft, there will be a muscle contraction so the athlete can move their arm to respond to the ball.